for permutation group, okay, first you have to know what is a permutation. So this is 1 to 1 and on to mapping. Can somebody define 1 to 1 to me? Who has not ticked yet? Today, okay. I don't need to choose the mixed mode student. Anybody can. Hassan, can you help us? What is a 1 to 1?
One-to-one proof a function is one-to-one if there is a one-to-one relation between the domain and codomain. For
Meaning if the two images are the same, okay, if two
yes,
images are the same,
then the elements are the same.
Okay, you cannot get like this. Different goes to 1.
Yes.
1 goes to different, that is not a function. Okay, you cannot have two images. So if you have two same one, you cannot have two different one. They have to be the same. This is the basic definition of 1 to 1. Okay, 1 to 1. What about onto? Somebody else can help me onto. Empty none. Do you remember what is an onto function? Or anybody can explain what it means by onto?
Onto means every pre-image has it can has two images.
Okay, it's not that easy to explain, right? From A to B, and you have F. Onto means for all B in B, for all, right? That exists A in A, such that FA is
equal B.
The key is here, it has to be for all. Okay, and that means onto. So that means this is one of the example, 1 to 1 and onto. If you have 4 here, you have to have 4 here. Okay, you cannot have an extra, because if you have this, it's not onto. If you have here, it's not a function, because everyone in here has to have an image. Okay, and onto means everyone here has to have the pre-image. Okay, so by this, meaning it has to have the same order. Okay, the set has to have the same order. But that is the basic definition of permutation. Okay, now if you look at chapter 4, when I define permutation group, given a set A, a permutation group is a set consists of all permutation. Given a set A, so this is permutation group. Given a set A, then a permutation group is a set containing all permutation, or consists of. On A. Okay. that forms a group under composition. Okay, under composition. Okay, as an example, actually you have seen this before. Okay, you have seen this before, so I just do this again. Suppose you have, I do this is easier. Okay, this is a set A, 1, 2, 3. This one, we call it E. Is the identity mapping, right? How many permutation that you can have? So, because there are 3 of them, for the first one, we can have 3 choices. 1 can go to 1, right? Starting can be from 1 to 1, 2 to 2, 3 to 3, 3 choices. After that, there will be 2 choices to choose. After that, there will be 1, so there will be 6 kind of permutation. So you can have this one, we call it, in the cycle form, it's 1 to 1, 2 to 2, 3 to 3, right? That's one of these. Another one is 1 goes to 2, 2 goes to 1. So we do like this. 1 goes to 2, 2 goes to 1. 3 goes to 3. Another one is 1 goes to 3, 3 goes to 1, 2 goes to 2. Another one is 2 goes to, 1 goes to 1, 2 to 3, 3 to 2. That's another one. So this means we fix 1. This means everything is fixed. This means we fix 3, 1 goes to 2, 2 goes to 1, like this. So this one we fix the 3, and then you change this. This one you fix the 2, then you change. So this is all still 1 to 1 and onto mapping. Or you can change all. This means 1 goes to 2, 2 goes to 3, 3 goes to 1. So when I write like this, it's a cycle notation. 1 goes to 2, 2 goes to 3, 3 goes to 1. So this is what I mean by 1 to 2, 2 to 3, 3 go back to 1. This is the same as writing 2, 3, 1. But I normally will start with the smallest number. Or this can be also 3, 1, 2, right? They are all the same. 1, 2, 3, or 2, 3, 1, or 3, 1, 2. So it's not unique. It can be all this. Okay, so we have 1, 2, 3. We have another one, right? Because we have 6, 1, 2, 3, 4, 5. Or you can go 1, 3, 2. 1 goes to 3. 1 goes to 3. 3 goes to 2. 2 goes to 1. So we have 6 of them. So this is called S3. Symmetric group on 3. Normally we call it letters. You can use ABC, but normally we use letters. Okay. So all this, when I write, okay, this is another way to write it. This is called matrix notation. Which is also just now. We don't write 2, 2, 3, 3, 4, 4, 5, 5. You just write 1. 1 means you don't see the numbers. It means 1 to 1, 2 to 2, 3 to 3. You just put 1 to 1. So this is the identity. And then maybe you can call it alpha. 1 goes to 2, 2 goes to 3, 3 goes to 1. This is 1 goes to 2, 2 goes to 3, 3 goes to 1. So this is called matrix notation. This is called cycle notation. So we put S3 equal 1, 1, 2, 1, 3, 2, 3, 1, 2, 3, 3, 2, 1. And how do you show this is a group? You can write the Kelly table. Okay, so without even writing the Kelly table, if I ask you, what is the identity? So this is the identity. How do you multiply? Okay, now how do you multiply? Like this. 1, 2 times 1, 3. I multiply from the right. I don't know if you learned before from the left, but I multiply from the right. Meaning I have to go from the right, 1, right? 1 goes to 3. There is no 3, so I stop at 3. 3 goes to 1, 1 goes to 2. 2, and 2 goes to 1. So this is how you multiply them. Then you have to try and redo this. Suppose you want to multiply using this notation. Suppose your beta is, just now this is 1, 2, 3, right? Suppose 3 is fixed. This is 1, 2. Okay, when you multiply this way, I don't like using matrix because you have to copy this. Okay, what you do is from the right. 1 goes to 2, 2 goes to 3. 2 goes to 1, 1 goes to 2. 3 goes to 3, 3 goes to 1. This is actually 1, 2, 3, 3, 1. Okay, this is how you multiply by matrix. If you multiply using this, you will get, start from 1 on the right, 1 goes to 2, then you jump, 2 goes to 3. There is no 3 here, so 3 goes to 3 here, 3 goes to 1. This is right. There's already 1 here, you close. But you have to check 2. 2 goes to 1. 1 goes to 2. So you get the same answer. So this is how I multiply. So you have to practice and write out the Kelly table of S3. Okay. Exercise. Just for you to probably remind you again what is S3. Okay, so what you will see throughout these chapters is to find the order of the elements, in the symmetric group. It's very easy. If you have the order of any, oh sorry, I cannot use alpha inside because I call it alpha. So I use A1, A2 until AN. Okay, so this is just N. So the order of 1, 2, 3 is just 3, it's just the length. Because 1, 2, 3 times 1, 2, 3 times 1, 2, 3, it will go back to 1. Okay, it's a cycle. You move again, how many the length? It will get equal to 1. So the length is just N. So just now, I erased, but S3 will have identity of order 1. 1, 2, 1, 3, 2, 3 has order 2. 1, 2, 3, and 2, 1, 2, 3, and 1, 3, 2 has order 3. So then you can see it's not a billion. 1, 2 times 1, 3 is different than 1, 3 times 1, 2. It's not. So you get all the properties of groups in there. Okay, so you have to go, take S3, go back to chapter 1, 2, and have to know all about S3. So you now have the order, you know it's not a billion. Definitely not cyclic, not a billion. And also because of, there is no element of order 6. Only element of order 1, 2, or 3. Okay, dividing 6. and you have to find the center. What do you think is the center of S3? You will see that the only element in the center is the trivial subgroup. Okay, only the identity. Everything else, they don't commute. Okay, so this is center. And also you have to find all the centralizers. Okay, what commute with that particular one. Then you will see the centralizer of 1, it commute with everything. So the centralizer of E is always the whole group. The centralizer of 1, 2, the only thing that commute with 1, 2 is 1, 2. 1, 3 is 1, 3, 2, 3 is 2, 3. The centralizer of 1, 2, 3 actually has order 3. The one that commute 1, 2, 3 is 1, 3, 2. So they are inverses. Okay. So one thing that I don't mention last time is that if the order of an element is 2, it is the inverse. And why is that? It's very easy, right? So you multiply both sides by A inverse, right? Okay. A is A inverse. Okay? And now, Syam, you have to tell me if you cannot read or see anything in the Zoom. Or if I put it anywhere. Please. Okay, guys? Is that okay so far? This or this? All right, okay. So what about the order of alpha, beta, gamma, 3 different? Okay, so this is the LCM of, if you have of alpha, beta, something like this. Okay, so if you have, okay, let me see. Okay. I didn't mention about this yet. This is alpha, beta, gamma, disjoint cycle. Disjoint cycle means there is no common number in between them. Okay? So like 1, 2, 3, 4, 5, 6. Disjoint cycle. Okay? 1, 2, 3, 4, 5, 6. So what is this order? The order is LCM, lowest common multiple. Lowest common multiple. 2, 2, 2, right? 2, 2, 2. So it's 2. That is the order. Okay. If you have something like this, what is the order of 1, 2, 3, 4, 5? Vian? What is the order of this?
3.
Okay. And this?
2.
Okay. And this is the answer is?
2.
The lowest common multiple of 3 and 2.
2. 6.
6.
I think.
Okay. Okay. Next question is the order of okay. Imanina. What is the answer? This is LCM of
3.
3. 3 and
3 and 2.
2.
2. Ah,
Why 2? What do you have to do? Okay, first, this is not disjoint, right?
mm,
It's not disjoint because there is a 2 here, there's a 2 here, there's a 1 here, there's 1 here. So you have to multiply first.
oh,
Okay, can you multiply, Iman? 1 to 2, 2 to 5.
5.
5 to 5, 5 to 1.
1.
2 to 3, there's no 3. 3 to 4, there's no 4. 4 to 1, 1 to 2. Okay, so this is LCM 2 and 3, which is 6.
Oh,
Okay. Okay, so meaning if you want to find the order of the elements in the permutation group, you have to make sure that they are the disjoint cycle. I usually say disjoint cycle. Okay. Okay, now look at the theorem. Every permutation is a product of disjoint cycle. Okay, you can always multiply out and you can always write as a disjoint cycle. And the multiplication of disjoint cycle commute, alpha beta is beta alpha if they are disjoint. Okay, so you don't multiply if they are not disjoint. If they are disjoint, you can multiply. Okay, now a new definition is transposition. Our Zoom now is limited. Okay. If we get disconnected, Hannah will give us a new link, yeah? Because I cannot use the other Zoom, the office Zoom. This Zoom is limited. So if we get disconnected, it's okay. We all will get disconnected. We have about 20 minutes, but remaining time is only 5 minutes. Okay, I just want to finish a little bit more about transposition. Is a 2 cycle. Okay, transposition is a 2 cycle. Somebody was asking me about Google Meet just now. Is it Lava? In the group? I haven't finished reading.
Tan.
Tan. Oh, what was the question? Because just now I cannot connect my camera with that Meet. That's why. Okay, anyway, transposition is a 2 cycle and every permutation can be written as a product of 2 cycle. Tadi dah ambil belum? Okay, so like A1, A2, A3, A4. How can you write this as a 2 cycle? What is it? A? Shyam, you remember? A1, A4, A1, A3, A1, A2. Okay? So you can write S3, for example, 1 is a 2 cycle. 1 is 1, 2, 1, 2. Right? 1 is 1, 2, 1, 2. And then we have 1, 2. Then we have 1, 3. And 1, 2, 3 is 1, 3 times 1, 2. So 1, 2, 3 is 1, 3, 1, 2. You can multiply back 1 to 2, 2 to 2, and so on. Okay? So this is the formula. A1, A4 A1, A3, A1, A2. Okay, so why we need to write permutation in terms of 2 cycle? Why? Because next is we have even and odd permutation. Okay, and even permutation is a permutation that can be written as a even number of transposition. Even number of transposition. Like this. Even 1 and 2. 2 is even. So this is even. Okay. And odd permutation is a permutation that can be written as odd number of transposition. So 1, 2, 3, 4 is odd permutation. Odd permutation. All right. 3 of them. So if n is odd, right? See, 4 is odd. Even if n is odd. Odd is n is even. Okay? And the identity is always, I said just now, even. Because you can write 1 as this. Or any 2 you multiply. Or you can even write like this. Oops. Or you can even write longer. Okay, as long as even number of transposition. Okay. So we are almost done actually. Less than 1 minute. Okay, anyway, you collect all even permutation, it becomes alternating group. So alternating group is the set of all even permutation. Okay.